Building infrastructure on Mars presents an array of technical, environmental, logistical, and human challenges that far exceed those encountered on Earth. The Martian environment is extremely hostile to human life and conventional construction techniques, with conditions that include a thin carbon dioxide-dominated atmosphere, extreme temperature fluctuations, high levels of radiation, reduced gravity, and frequent dust storms. Any infrastructure intended for long-term human habitation, scientific research, resource extraction, or industrial production must be designed to withstand these conditions while ensuring the safety, comfort, and productivity of its occupants. Unlike Earth, Mars lacks a readily available supply of many materials traditionally used in construction, requiring that they either be transported from Earth at great cost or produced locally using advanced in-situ resource utilization technologies. The balance between minimizing cargo shipments from Earth and maximizing self-sufficiency on Mars will shape every stage of planning and construction. The reduced gravity on Mars, approximately 38% of Earth's gravity, has both advantages and disadvantages for infrastructure development. On one hand, lower gravity means that structures can support more mass relative to their material strength, allowing for larger and potentially lighter designs. On the other hand, the long-term effects of reduced gravity on human health, including muscle atrophy and bone loss, necessitate the inclusion of specialized exercise and health maintenance facilities within any habitat. Additionally, construction techniques that rely on gravity for stability or material handling, such as pouring concrete or using cranes, will require adaptation to ensure they function reliably in the Martian environment. Radiation exposure poses one of the most significant threats to infrastructure design on Mars. Without a strong magnetic field or thick atmosphere, Mars offers little protection from cosmic rays and solar particle events, which can cause serious health problems and degrade materials over time. Shielding against radiation will be a critical requirement for all living and working spaces, potentially achieved through burying structures beneath regolith, constructing walls with thick layers of Martian soil, or using materials infused with hydrogen-rich compounds. Some concepts also propose using ice as a radiation shield due to its excellent protective properties, but this would require reliable methods of ice extraction, storage, and integration into building materials. Temperature extremes are another major challenge. Mars experiences daily and seasonal temperature swings far greater than most locations on Earth, with surface temperatures varying from about 20 degrees Celsius during the day near the equator to below 100 degrees at night. These fluctuations can cause thermal stress on structural materials, leading to cracking, warping, and fatigue over time. Thermal insulation will be essential to maintain stable internal conditions for habitats and operational facilities, with solutions ranging from multi-layer insulation panels to vacuum-sealed compartments. Heating systems must be highly efficient and powered by reliable energy sources, as failure to maintain temperature control could have life-threatening consequences. The Martian atmosphere, being less than 1% the density of Earth's and composed primarily of carbon dioxide, presents unique engineering problems. Pressurized habitats will need to withstand significant pressure differentials between interior and exterior environments, requiring airtight seals, robust structural integrity, and meticulous leak detection systems. The lack of atmospheric pressure also means that unprotected water boils away quickly, and traditional fluid-based construction methods are impractical without specialized containment. Any infrastructure must be designed with airlock systems to prevent depressurization and to manage the entry and exit of personnel and materials safely. Dust is a pervasive and persistent hazard on Mars. The planet's surface is covered with fine, electrostatically charged dust particles that can infiltrate mechanical systems, abrade equipment surfaces, and pose respiratory risks if inhaled. Dust storms can last for weeks or months and reduce visibility to near zero, while also limiting solar power generation. Infrastructure must be designed to resist dust infiltration through the use of seals, filters, and protective coatings. Maintenance systems will need to regularly remove dust from solar panels, ventilation systems, and moving parts to ensure continued functionality. Power generation and distribution are central to Martian infrastructure, yet both are complicated by environmental constraints. Solar power is readily available but subject to fluctuations caused by dust accumulation and seasonal changes. Nuclear power offers a more consistent energy source, but requires complex safety protocols, reliable shielding, and careful waste management. Wind energy is less viable due to the thin atmosphere, though some designs propose specialized high-efficiency turbines for supplemental power. Energy storage solutions, such as advanced batteries or regenerative fuel cells, will be critical for maintaining operations during periods when primary generation systems are compromised. Water supply is another foundational requirement for building and sustaining infrastructure on Mars. While there is evidence of significant water ice deposits beneath the surface and in polar regions, extracting it poses technical challenges. Techniques such as heating regolith, drilling into ice-rich layers, or using chemical processes to release bound water will require specialized equipment and substantial energy. Once obtained, water must be purified, stored in insulated containers to prevent freezing, and recycled extensively within closed-loop systems to minimize losses. Water is not only essential for human consumption, but also for agriculture, oxygen production, and potentially as a construction material. Material sourcing and production on Mars will likely depend heavily on in-situ resource utilization. Martian regolith can be processed into building materials such as bricks, concrete-like compounds, or sintered blocks using heat and pressure. Technologies like 3D printing could allow for automated construction of large structures with minimal human intervention, reducing the need for heavy machinery and lowering the risks associated with manual labor in a hazardous environment. However, regolith contains toxic compounds such as perchlorates, which must be removed or neutralized before use in habitats or agricultural systems. Metallurgical processes to extract iron, aluminum, and other useful elements from local minerals will require specialized reactors and significant energy input. Transportation and mobility on Mars will influence both the pace and scale of infrastructure development. Surface vehicles must be capable of traversing rough terrain, operating in low temperatures, and resisting dust contamination. They will be essential for transporting construction materials, equipment, and personnel between landing sites, storage facilities, and building zones. Autonomous or remotely operated machinery could reduce risks to human workers and allow for construction to proceed even in hazardous conditions. Though communication delays with Earth mean that high levels of onboard autonomy are necessary. Life support systems are the backbone of any inhabited infrastructure on Mars. They must maintain stable atmospheric conditions, including oxygen levels, carbon dioxide removal, humidity control, and temperature regulation. These systems must operate continuously with minimal downtime, requiring redundancy, fault tolerance, and easy maintenance. Waste recycling, food production, and water reclamation systems will need to be integrated into the infrastructure from the outset to achieve long-term sustainability. Any failure in life support could have immediate and catastrophic consequences, making reliability a top priority. Communication infrastructure will be vital not only for coordination between different Martian facilities, but also for maintaining contact with Earth. Given the time delay of several minutes each way, systems must be designed to handle asynchronous communication, data storage, and automated decision-making. High-bandwidth communication satellites, ground stations, and relay towers may need to be established to ensure constant connectivity across the Martian surface. These systems must be robust against dust storms, power outages, and mechanical failures. Safety and emergency response capabilities will play a major role in the design of Martian infrastructure. Unlike Earth, where rescue operations can often be mobilized quickly, Mars offers no such immediacy. Facilities must therefore be designed to handle medical emergencies, equipment failures, and environmental hazards independently. This could involve multiple redundant habitats, safe zones with independent life support, and stockpiles of critical supplies. Training for all personnel in emergency procedures will be essential, as well as incorporating automated monitoring systems to detect and respond to problems before they escalate. Psychological and social factors will also impact the success of Martian infrastructure. Long-term isolation, confinement, and limited interaction with the outside world can affect mental health, productivity, and group dynamics. Infrastructure must provide private spaces, recreation areas, and opportunities for meaningful work to support emotional well-being. Lighting, interior design, and environmental cues that mimic Earth-like conditions could help reduce stress and maintain morale. The layout of facilities should encourage social interaction while also allowing for personal space. Over time, the expansion of infrastructure will create new challenges in governance, maintenance, and resource allocation. Decisions will need to be made about who controls access to certain facilities, how resources are distributed, and how disputes are resolved in the absence of Earth-based legal systems. As settlements grow, they will require more complex logistical networks, supply chains, and administrative structures. This evolution will mirror the growth of cities on Earth, but with far more limited resources and higher stakes for survival. Environmental stewardship will be another important consideration in Mars infrastructure development. While Mars may not host complex life, the principle of planetary protection demands that human activity minimize contamination and preserve the natural state of the planet for scientific study. Waste disposal, pollution control, and sustainable resource use will need to be integral to planning and operations. Any accidental release of biological material could compromise future research into Martian life and violate international agreements. Ultimately, the challenges of building infrastructure on Mars are intertwined and must be addressed in a coordinated and systematic way. Success will depend on a combination of technological innovation, careful resource management, robust safety measures, and the ability to adapt to unforeseen problems in an environment that offers little margin for error. The experience gained from building and maintaining such infrastructure will not only determine the viability of long-term human presence on Mars, but will also inform humanity's broader ambitions for colonizing other worlds.